Welcome to my presentation about accelerating the neural network inference with a customized RISC-V extension. Today we are going to talk about a healthcare application, more specifically the detection of atrial fibrillation in a patch ECG device. First, I will introduce the Artemis research project to you. Then I will talk about the data we used to train the neural networks as well as the neural network structure. We will also talk about the approaches for acceleration. It's mainly two approaches. First, the activation functions and the nodes of the neural networks, and then the single instruction multiple data operations for the multiplications. We will also talk about the impact on the required hardware resources on an FPGA as well as for an ASIC synthesis. The performance of the neural network will be presented at the end to show what we've achieved so far. Artemis stands for AI-based real-time detection of atrial fibrillation and integration into a wearable medical sensor device, the so-called patch ECG, which is more or less like a band-aid, so really lightweight and low power. It is a project funded by the German Ministry of Research and Education. The main targets are to make the device capable of operating autonomously up to 14 days, to collect and evaluate ECG data on the patch itself, which means we have to work without a backend server and therefore have to use an embedded AI and really efficient hardware to achieve the long operating time. Therefore, we try to accelerate the computing effort using customized accelerators and therefore reduce the clock frequency and resulting NSE consumption. The accelerators will increase the hardware resources, therefore it's a bit of a trade-off to find the optimal solution. Our partners in the project are GTMed, Charité Universitätsmedizin Berlin, Scient and Syneos. For Artemis we will use two Fraunhofer intellectual properties. One is the RISC. It's a RISC-V based processor optimized for embedded AI. Basic version is available now under SolderPad license on GitHub. It is focused on safety applications, embedded AI, cryptography, and many more possible applications. It is meant to be used as an FPGA solution as well as an ASIC synthesis. The other thing is IPS, AI for Embedded Systems. It's a software framework also focused on embedded AI for inference as well as training, and it's basically free for non-commercial use and there are commercial licenses available. The RISC is based on a classic 4-stages pipeline, and as you can see in the execute stage of the pipeline there's a PCPI interface, which is the Pico coprocessor interface that allows to connect arbitrary coprocessor extensions, so any type of extension you want to connect with the microcontroller. With this interface, the pipeline can be stopped using a wait and ready signal, so you have a high flexibility for custom extensions and you can take as many clock cycles as you need for your customized accelerators. For the Artemis project, Charité provided us with 22,400 ECG recordings that were acquired in a clinical trial with about 350 patients. 16,000 of the ECG recordings are used for training of the neural networks, and 6,400 datasets are used for validation of the neural networks. The neural networks we use in this project are so-called micronets, which are small, light-weighted neural networks. They have one hidden layer and of course input and output layer. For the micronets we use a quantized data type, quantized to 8-bit fixed point integer, also called Q7, which also reduces the memory and computing effort on our system-on-chip solution. The structure of the neural network is 13 input features, which are basically representing distinct peaks of the ECG signals, distinct time windows, and also statistical processing. The hidden layer is equipped with 32 nodes, and as you can see we have a fully connected net, which means that every node in the input layer is connected with every node in the hidden layer, and every node in the hidden layer is connected to every node in the output layer. In the output layer we have two nodes that basically correspond to we have detected atrial fibrillation or we did not detect atrial fibrillation, using a softmix function for normalization. In the hidden layer, we have different activation functions that I will show you later, also because we have customized accelerators for several possible activation functions. Now I want to explain to you which approaches we chose for acceleration of the neural network inference in the hardware. First, I want to talk about the nodes. As you can see, there are many nodes in this neural network, and all of them have an activation function, which is usually based on a mathematical relation. In AI for embedded system, for example, Tangent, Sigmoid, and Softmix function are supported for these nodes. And in between the nodes, we have those lines. The lines all represent a multiplication with the weight and the value of the previous node. Therefore, it is also a valid approach to accelerate the multiplication using a single instruction multiple data operations that are able to compute several multiplications in parallel. As mentioned, one of the activation functions in AI for embedded systems is the hyperbolic tangent function. You can see the function as the mathematical function itself by the blue line on the right. And you can also see that it's a symmetrical function, which of course we used to reduce the hardware effort. Then we combined two approaches for the approximation. The first one is a linearization that you can see in the middle part of the picture. And we tried to keep the error below half a least significant bit so that the error has least impact on the performance of the neural networks. We also used a range addressable lookup table, which is the violet line on the picture, where you basically define all Y quantization steps to a X range to also reduce the hardware effort to a minimum and the error to a minimum. For the Sigmoid function, we tried to avoid having to implement the function itself from scratch. Therefore, we used the mathematical relation between hyperbolic tangent and sigmoid. And as you can see, the formula contains a division, but the division by 2 can also be implemented by a shifting operation. Therefore, we use 2 shifting operations in the schematic below, an addition of 1, and the tangent function from the previous slide. On the right, you can see the approximation together with the mathematical function, and as you can see, the error is also quite small. The softmix function is based on all the input values for the node. Therefore, it's difficult to implement the softmix function completely in a hardware module. But as you can see, it uses the exponential function, which can be accelerated using hardware. Therefore, we used the so-called Cordic algorithm. We used 8 stages that you can see on the right in the schematic, which basically compute the hyperbolic sine and the hyperbolic cosine. And by adding or subtracting the two of them, you can approximate the E function in the area between -1 and 1 for the input values. Now I want to talk about accelerating the multiplications, the lines in the neural networks. Therefore, we use single instruction multiple data operations, so-called SIMD operations, which are also part of the signal processing extension, P extension of RISC-V. We are processing 4 8-bit multiplications in parallel and write them into a 64-bit result. Therefore, in theory, we would get at least a factor 4 in inference speed. To implement the SIMD operations most efficiently, we splitted our multiplication unit into several submultipliers and combined them also together to still achieve a 32-bit multiplier. As you all know by the binomial formulas, if you split a value for multiplication, you get 4 multiplications and 3 additions to combine them together to the same result as before. So if we combine our 8-bit multipliers that we used for the 8-bit SIMD operations, we get a combined 16-bit multiplier. And if we combine two of the 16-bit SIMD multipliers together with an additional one, and the combined multiplier from the 8-bit SIMD operations, we can still achieve our 32-bit multiplication with minimal hardware effort. To get a first impression of the hardware resources needed, we used a field programming aggregator array. We used the Nexus Video Development Board, which has a RTX 7 FPGA chip. For the RISC core itself, we usually use 11,350 lookup tables and 4,550 flip-flops, which are then used as a reference for the customized extensions here. It operates on a clock frequency of 30 MHz. For the activation functions, so Hyperbolic Tangent, Sigmoid, and E function, we have an increase of 1.5% for the lookup tables and 0.9% for the flip-flops. For the single instruction multiple data operations, we have 12.4% for the lookup tables and 3.53% for the flip-flops. For the Artemis project, we did an ASIC synthesis to see the hardware resources needed in 180 nanometer XFAB technology. We used a clock frequency of 30 MHz to achieve a low power design, and we needed less than 1 square millimeter of silicon area, also less than 1 millimeter in width and height of the floor plan. This is a quite good value compared to other cores, as I put one in the references that needs 1.77 square millimeters in the same technology. We have 23,566 standard cells in the design, which have an area equivalent of 61,150 NAND cells, which is also compared to other cores quite a good value. So let's have a look on the performance of the neural networks. For the usual neural networks using software for the activation functions, we have the light blue color here. You can see that they are the highest in runtime and are about 63 to 67.5 thousand clock cycles. With the activation function accelerators, we can achieve up to 10% acceleration, which is presented in the dark blue colors here. You can see that the slight error in the approximations for the activation functions lead to a slight loss in F1 score, but still it's far above 80% in F1 score, which is quite good for such small micronets. Using the SIMD operations, we can achieve a factor of 6 or 7 in runtime, as you can see by the green colors on the left here. It's far more than factor 4 apparently, and the reason for this is basically that the memory operations are even further optimized when you are using the SIMD operations. So it's not only that we can compute 4 results in parallel, but the memory access is also accelerated slightly. Therefore, we have more than factor 4, we even achieve factor 6 or 7. Using both approaches, we can get a neural network that is the same structure, but only needs 9.5 thousand clock cycles, which is really, really low. Thank you for your attention. Here are my references that are used for the presentation, and of course I want to thank again the Charité Universitätsmedizin Berlin for the data and medical insights they provided for the Artemis project. Now I am open for your questions. Thank you.